A log periodic antenna. A log periodic antenna is a multi-element and directional antenna designed to operate over a wide band of frequencies. The most common, it was invented by John Dunleavy in 1952. The most common form is log periodic dipole antenna array. It consists of number of off-wave dipole-driven elements of gradually increasing length. Each consists of a pair of metal rods. The dipoles are mounted close together in a line connected in parallel to the feed line with alternating phase. Electrically, it simulates a series of 2 or 3 element Yagi-Uda antennas connected together, each set tuned to the different frequency. Log periodic dipole antenna looks somewhat similar to Yagi antenna in that they both consist of dipole rod and rod elements mounted in a line along a support boom. But they work in very different ways. Adding elements to support beam but they work in a different ways. Adding elements to the Yagi increases its directionality or gain, while adding elements to an log periodic dipole antenna increases its frequency responses or bandwidth. One large application is in rooftop terrestrial television antenna, since they may require large bandwidth to cover various frequencies in very high frequency band or upper high frequency band. Ultra high frequency bands. One widely used design for television reception combined a Yagi for ultra high frequency reception in front of a larger log periodic dipole antenna for very high frequency. Basic concept behind a log periodic dipole antenna, it normally consists of a series of off-wave dipole elements, each consisting a pair of metal rods positioned along a support boom lying along the antenna axis. The elements are spaced at intervals following the logarithmic function of the frequency known as d or sigma. The length of successive elements and the spacing between them gradually decrease along the beam. The relationship between the length is a function as known as tau. Sigma and tau are the key design elements of log periodic dipole antenna element design. The radiation pattern is unidirectional, with the main lobe along the axis of the boom, off the end with the shortest elements. Each dipole element is resonant at a wavelength approximately equal to twice its length. The bandwidth of the antenna frequency range over which it has near maximum gain is approximately between the resonant frequency of the longest and shortest elements. Every element in the log periodic dipole antenna is a driven element that is connected electrically to the feed line. A parallel wire transmission line usually runs along the central boom, and each successive element is connected in opposite phase to it. The feed line can often be seen as a zigzagging across the support boom holding the elements. Another support beam holding the elements. Another common construction method is to use two parallel central support beams that also act as the transmission line. ஆக்சுவலி இங்கே பூம்னு இருக்கிறது மிஸ்டேக்காக இருக்கும்னு நினைக்கிறேன். பூம்னு இருக்கிறது எல்லாம் பீமாக இருக்கும்னு நினைக்கிறேன். Mounting the dipoles on the alternative beams, other form of log periodic design, replaces the dipoles with the transmission line itself, forming the log periodic zigzag antenna. Many other forms using the transmission wire as the active element also exist. The Yagi and LPDA designs look very similar at first glance, as they both consist of a number of dipole elements mounted along the support boom. The Yagi, however, has only a single driven element connected to the transmission line, Usually, the second one from the back of the array, the remaining elements are parasitic. The Yagi antenna differs from the log periodic dipole antenna in having very narrow bandwidth. In general terms, at any given frequency, the log periodic design operates somewhat similar to the three-element Yagi antenna. The dipole element closest to resonant at the operating frequency act as a driven element, with the two adjacent elements on either side as director and reflector to increase the gain. The shorter element in front acting as the director and longer element behind as a reflector. However, the system is somewhat more complex than that, and all the elements contribute some degree, so the gain for any given frequency is higher than the Yagi of the same dimensions as any one section of the log periodic. However, a Yagi with the same number of elements as a log periodic would have far higher gain, as all of those elements are improving the gain of the single driven element. In its use as a television antenna, it was common to combine a log periodic design for VHF with a Yagi for UHF, with both halls being roughly equal in size. This resulted in much higher gain for UHF, typically on the order of 10 to 14 dB on the Yagi side and 6.5 dB for the log periodic. But this extra gain was needed anyway in order to make up for a number of problems with ultra high frequency signals. According to IEEE definition, the log periodic shape does not align with the broadband property for antennas. The broadband property of log periodic antennas comes from its self-similarity. A planar log periodic antenna can also be made self-complementary, such as logarithmic spiral antennas. The logarithmic spiral antennas, which are not classified as a log periodic per se, but among the frequency independent antennas that are also self-similar, are the log periodic toothed design. Wojciech found for what he termed the termed as the simplest self-complementary planar antenna, a driving point impedance of neta naught divided by 2 is equal to 188.4 ohm at frequencies well within its bandwidth limit. These are the different diagrams of different images of log period antenna. One which having the frequency of 250 to 2400 megahertz. Second, 140 to 470 megahertz. It is mounted for vertical polarization. Third image is a log periodic television antenna. 1963, it covers 54 to 88 megahertz and 174 to 218 megahertz. Slanted elements were used because on the upper band they operate at the third harmonic. Fourth image is wire log periodic monopole antenna. History of log periodic antenna. John Dunleavy invented the log periodic antenna in 1952 while working for the United States Air Force, but was not credited with it due to its secret classification. The University of Illinois at Urban Campaign had patented the Isbell and Myers-Carroll antennas and licensed the design as a package exclusively for JFD Electronics in New York. Channel Master and Blunder Tongue Clubs ignored the patents and produced a wide range of antennas based on the design. Lawsuits regarding the antenna pattern, which the UAE Foundation lost evolved into the 1971 Blender Tongue Doctrine. The president governs the patent litigation. Next one is shortwave broadcast antenna. The this image, first image, wireless periodic transmitting antenna at International Shortwave Broadcasting Station, which is located in Moosbrunn, Austria, which covers 6.1 to 23 megahertz. Schematic diagram of shows the second image shows the diagram of zigzag shortwave LPA antennas. Black shows metallic conductors, red shows black color shows metallic conductors in this diagram. Red color shows insulating supports. The log periodic is commonly used as a transmitting antenna in high power shortwave broadcasting stations because its broad bandwidth allows a single antenna to transmit on frequencies in multiple bands. The log periodic zigzag design with up to 16 sections has been used. These large antennas are typically designed to cover 6 to 26 megahertz, but even larger ones have been built which operates as low as 2 MHz. Power ratings are available up to 500 kilowatt. Instead of the elements being driven in parallel attached to the central transmission line, the elements are driven in series. Adjacent elements are connected at outer edges. The antenna shown here would have about 14 dBi gain. An antenna array consisting of, here dBi will be used where I shows the isotropic nature. 14 dBi gain. An antenna array consisting of two such antennas, one above the other and driven in phase, has a gain of up to 17 dBi. Being log periodic, the antenna's main characteristic radiation pattern, gain, driving point impedance are almost constant over its entire frequency range, with a match to a 300 ohm feed line impedance, 300 ohm impedance feed line, in achieving a standard wave ratio of better than 2:1 over that range. These are the reference papers.